We're going to start our next section today, 4.3, and we're going to spend quite a bit of time today looking at these connections a little bit further.
Should I go to like a different classroom or just stay This is it all.
Okay, we're going to spend more time today looking at these characteristics a little bit further, but we're specifically going to highlight kind of vertical asymptotes and holes today. Yesterday was more along the lines of restricted values, x-intercepts, y-intercepts. Okay, but we're just going to keep adding to this list of characteristics and criteria that we can pick apart from a graph. Now, kind of as a review, we have already seen holes and vertical asymptotes a little bit this year. Okay, not as heavily as this unit is going to cover, but holes and vertical asymptotes, we've noticed how those are places on the graph where a point does not exist, meaning the graph itself is discontinuous. Okay, there's some point that's not there. There's no way that a graph is like completely connected or filled in. So something special is going on. And we've talked about continuity earlier this year, but we're just going to kind of add on to that in this section. So in terms of being discontinuous, we can have three different types. Sometimes it's referred to as a point, but we're commonly referring to that in here as a hole. Okay, so you might have an open circle somewhere on your graph. You might have what's called an infinite discontinuity, but we're calling those vertical asymptotes. And then the third type is a jump. Okay, these don't really show up in rational functions, but we have seen jumps previously this year, okay, where we have kind of that disconnect within our graph. So in our own words, I'm curious if we can go ahead and jot down a description of what the graph would look like at these three different spots. If you take a look at the pictures below kind of as a guide, notice how this hole happens at 1, this vertical asymptote happens at 1, and this jump happens at 1. So they're all happening at the same value, but if someone were to ask you, hey, what does a hole look like on the graph, how would you describe that to them? Can we do it in your own words? Yeah.
Negative and positive x approach the same y value, but they never like actually meet at that y value.
Okay, so when you say negative and positive, do you mean like from both sides? Yeah. Okay, so both sides come to the same y value, right? But the y value itself,
like at that x value, there is no point.
There's no point. Okay, so perfect. So the left and the right meet up, but if there's no point there, if there's no xy there, they'd meet up at an open circle. Notice how that fits this description. Okay, the left and the right look like they would meet, but they're meeting at an open circle. So left and right meet at an open circle. I hope that description kind of sounds familiar because that's actually how we described the location of a hole previously this year, towards the beginning of the year. Now, if we were to use that same description, notice how it would not fit the middle graph. Okay, we do not have the left and the right side of 1 meeting up in an open circle. So how do you want to describe what a vertical asymptote looks like? Can we describe what the left and right are doing? Yeah?
The left and right come infinitely closer to a y value, but they never meet.
Closer to an x value. Okay, so the left and right, if you're getting infinitely close to something, that means you're approaching it. So I'm just going to use approach just as a shorter word. Okay, infinitely get closer to, or basically approach an x value, but never reach it or touch it. So if you're getting infinitely close to something, okay, you're eventually going to have to start to level a little bit. If you're reaching it but you never actually get there, notice how the left-hand side is eventually going to go up forever because it's leveling that way, and then the right side in this case would level downward. Okay, so the left and the right side are doing something different for an asymptote than what they're doing for a hole, and we can see that based off the picture. How can we describe a jump location? Okay, what can we say about the left and right sides? If we look at this graph, it doesn't fit the open circle definition because the left and right definitely don't meet. And it doesn't fit the vertical asymptote description because on this right-hand side we actually do reach the x value of 1. So there has to be some other description that we can use for a jump. How would you describe it? Left and right are doing what? Go ahead, Maggie.
Not connected.
Not connected. Okay, or they don't meet up. So we don't have that invisible dotted line like an asymptote has. Okay, so we clearly don't see that. But the left and the right aren't connected at all, so it doesn't really fit that description of a hole. So we have 3 different types of discontinuities, and depending on what you notice in terms of the description, you can classify them as either a hole, a jump, or an asymptote. So for rational functions, though, we're going to focus a lot more on holes and vertical asymptotes. Jumps usually only happen in piecewise functions. Okay, and we dealt with those earlier this year. Okay, but today, or in this unit, we're going to focus on holes and vertical asymptotes. Let's try to just, for review, practice domain and range for a little bit. So for our first graph, if we were to trace it left to right, notice how we have an arrow going to the left. So it'd be negative infinity. As we drag our pencil across, we encounter an open circle at 1, which means there's no point there at that location. So we're going to have to skip over the number 1. After the hole, though, we're kind of home free because there's nothing else that would make us stop lifting up our pencil. And we have an arrow on the right-hand side, so we'll go to positive infinity. Let's try the same thing for the range. So we'll drag our pencil low to high. We have an arrow going down, so negative infinity. As I drag my pencil up, I eventually reach the hole, but is there another point that exists at that same height as the hole? Yeah, it's actually somewhere to the right a little bit. Okay, so even though there's an open circle there, notice how you still are able to include that range value, that y value, because a point exists somewhere else. So as long as you have a point somewhere, you're good to go, which means we can keep tracing. And as I continue to trace, I eventually encounter another arrow going up forever, so positive infinity. All right, let's try the next one. So domain, left to right, arrow going to the left, negative infinity. As I drag my pencil to the right, I encounter a vertical asymptote, meaning no physical point at the x value of 1. So I'm going to have to skip over that. And as I continue to drag, I'll get an arrow on the right-hand side, which would be positive infinity. If we check out the range, low to high, I have an arrow going down, so negative infinity. And as I drag my pencil up, notice how I'm always touching a point on the graph. And I'll eventually reach an arrow going upwards forever, so that would mean positive infinity. All right, for our last one, we can go negative infinity to the left. As I drag my pencil across, I encounter an open circle at the x value of 1, but is there another closed point somewhere else at that spot? Yes, somewhere up here. So I don't have to skip 1 because there's another point existing somewhere else. That means I can continue to drag, and I'll eventually get an arrow on the right-hand side, so positive infinity. If we do the range, we have an arrow going down, so negative infinity. As I drag my pencil up, I encounter an open circle, but there is another y value at that spot, so I can keep dragging. And I'll eventually encounter an arrow, which means I'll go up forever. So what's a little neat, if you notice, how all of these graphs were discontinuous at 1, okay, whole vertical asymptote jump, but notice how the jump actually had a domain of all real numbers, okay, whereas in the previous 2 we had to skip over that discontinuous location. So just because you're discontinuous doesn't mean you have to skip over certain locations, okay? It's all about whether you have a point there or if you don't. So you can't really just make that assumption. You have to be a little careful. Okay, coming back to us a little bit. Discontinuities. Okay, we're going to see a lot more of them today when we take a look at these graphs. So our goal today is to start to get used to analyzing different characteristics, just like we've done in the past, but we're really going to start to focus on how those characteristics are related to the equation. We did a little bit yesterday when we did the chart, but we're going to take a look at a few more today. So let's take a look at this rational graph, and they give us the function at the top. They also tell us that the coordinate of the whole is 3,7/5. So that might be interesting or needed for us in the future. Looking at the first one, it's asking us, as the x values get really, really negative. So if your x's are getting really, really negative, that means you're moving to the left, okay, on the graph. So can we think about, as this graph moves to the left, can you describe what the y values are doing, aka f of x values? If you were to trace your graph forever to the left, can you describe what's happening? What are the y values doing? When you think about it, let's see, at -3 my y value is 5. At -5 my y value looks to be about 3. At -9 my y value looks to be 2.3, 2.2, something like that. What's happening to the y values if I keep going to the left? What do you think, Caitlin? They're decreasing. Are they going to decrease forever? Are they going to go down to negative infinity? They are getting smaller, but how are they getting smaller? They're getting closer to 2. Okay, so the y values we'll say are getting closer or are approaching 2. All right, let's try the right-hand side. So as the x's get really, really big, I want you to trace the graph on the right-hand side, and if you were to continue to go to the right forever, what would the y values do? What are they approaching? What are they getting closer to? Do we see how it's 2 on that side as well? Okay. So instead of just looking at the end behavior, okay, what the ends of the graph are doing, we can start to pinpoint what the graph is doing at a particular location. So that's where the next one's going to come in. What if we were to approach the x value of 3 from the left? Sometimes you might see a little negative sign after the 3, which signifies the left-hand side. That's a little bit more of a calculus notation, but sometimes the negative might be there instead of the words. So let's find, first of all, the x value of 3, which is right here. And as you trace from the left, okay, to the x value of 3 on the graph, notice how you're getting closer and closer to the whole. and the whole has a y value of 7/5. Okay, they told us that at the top. They also want us to check out to see what the graph does from the right-hand side of 3. So sometimes you'll see a little plus there. If we trace from the right, okay, to that x value of 3, bless you, notice how the right-hand side is also getting closer to the whole. So that side would also be 7/5. Does that make sense based off our definition? Didn't we say the left side and the right side have to meet at an open circle? And if they're meeting, don't they have the same height? Okay, because if they don't meet, that would mean they have a different height. Okay, so it makes sense that both of these would be the same value. Let's try a different spot. So we'll do -2 from the left. Here's the x value of -2. If we trace from the left-hand side, notice how the graph is going to go up forever because we have that vertical asymptote there. So we can say that the y values are getting increasingly larger forever, okay, positive infinity. And if we trace from the left-hand, or from the right-hand side rather, the graph is going down forever, so we'll have negative infinity. Okay, so we're just getting used to this behavior based off of a graph, but eventually we can apply the same behavior to a table. Okay, we'll probably see an example of that tomorrow. Let's go ahead and try domain and range for this one like we did the previous ones. So if we trace from left to right, we have an arrow to the left, negative infinity. As I drag my pencil across, I encounter a vertical asymptote. There's no physical point there, so I have to skip over it. As I continue to drag, I encounter a hole at 3. There's no physical point there either, so I have to skip over it. And after 3, we're kind of good to go the rest of the way because we get to that arrow. So it goes from 3 to infinity. Bless you. For the range, okay, low to high, we have an arrow going down forever, so we'll have negative infinity. As we drag our pencil up, we encounter that hole. And if we're doing the range, this would be a y value. So the y value of the hole, they told us, was 7/5. So we're going to skip over that. As I continue to drag, though, I get to that horizontal asymptote. Okay, something we approach, but we're never going to touch on the ends. So we're going to have to skip over 2. And after 2, we're good to go because we eventually get an arrow. Okay. So it seems like for these rational functions, whenever we're writing a domain and range, we're going to have to skip over any asymptote location, okay, vertical or horizontal, and we're going to have to skip over a whole location, meaning the x value and the y value. Okay, because remember, domain is x, range is y. So we have to bring both of those into consideration. Are we doing okay with our first one? Okay, let's go ahead and try another one. Do you guys want to give it a shot? See if you can do it? Okay, try the left-hand side, the right-hand side. -3 from the left and the right, 1 from the left and the right, and then do domain and range. When we're done with that, we'll check it, and then we'll start to go over some characteristics.
saw the scene where I don't see that force and I'm trying to do it about it. I think he just don't get it. That's what I was saying.
Oh my god.
I'm trying to movie, I thought you could just stay ready. That's why I was so stuck up on the idea.
That's why I was disproving your theory. I was like, no, he killed himself. No, but that'd be too obvious. Show it, so.
All right, looks like we're good to go. Matt, can you do our first one? Negative, if you go to the left forever, what's happening?
No, you get closer to 1.
Closer to 1. All right. Caitlin, can you do the right one? 1 as well. Okay. Hadley's not here. Travis, -3 from the left.
The approach is -1/2.
Okay, so
-1/2.
Okay, so on the left-hand side of -3, we're going to get closer and closer to the hole, which has a height, okay, y value of 1/2. Good. Carter, can you do the -3 from the right?
It also proves one.
There we go. Okay, if it's a hole, you know you got to have the same height on both sides, so the left and the right should be the same. All right, Robbie, can you do 1 from the left?
It approaches negative.
Negative infinity. Okay, so here's 1. If you trace the left-hand side of the graph, you're going to go down forever. Looks good. Olivia, what about the right-hand side? Positive infinity. Good. Right-hand side goes up forever. How do we do on those 6? Good? All right. Blake, can you tackle the domain for us?
-∞ to -3.
Okay.
-3 to 1, and then 1 to infinity.
I love it. Okay, so -3 and 1 are those discontinuous vertical asymptote and hole locations. So we have to skip over those because there's no physical point there. Looks good. Elsie, can you tackle the range? Okay. I love that too. Okay, so if we have asymptotes and holes, we have to make sure we skip over them both times. So 1/2 is the height of the hole, and 1 is the height of the horizontal asymptote. Okay, so we have to skip over that one as well. How do we do? Pretty good? Okay, so what we're going to do, I know there's some more graphs on the next page. We'll get to those in a minute. I want to take a second and take a look at these 2 examples a little bit more to see if we can start to get a connection between the way the graph looks and the function itself. So in order to do that, we're going to do some our algebra techniques like we did yesterday, for instance, factoring, to help us get some of that information. So for this first one, if we factored 2 numbers that multiply to 3 but add to 4, we'd have x plus 3, x plus 1. For the bottom, 2 numbers that multiply to -3 but add to 2, x plus 3, x minus 1. So I'm curious, okay, can we make a connection between where a hole is located and where a vertical asymptote is located based off of the factors of the function? Graphically, we can tell there's a hole at -3 and a vertical asymptote at 1. So how are the factors telling us that those discontinuities are happening in those spots? How do we know -3 is a hole, and how do we know 1 is a vertical asymptote? What do you think?
Well, the fact is that the denominator will, first of all, show us the points.
Okay, so the numbers that make the bottom 0, -3 and 1. So we know something's going on there, either a hole or either a vertical asymptote. How can we look at the function a little further to determine exactly what's going on at -3 and exactly at 1? Yeah.
Since there's a repeat of the 3 in the numerator, that means that it's a hole.
Right, because if -3 makes the top 0 and the bottom, okay, 0 over 0, we previously stated that that was kind of a characteristic of a whole. So notice how the x minus 3's would essentially cancel each other out if we're dividing. It's a fraction after all. So we'll go ahead and write down at the bottom that canceling factors create wholes. So after you factor it, if you notice a repeat, okay, something in the top that's also in the bottom, we know we have a whole at that spot. So we'll go ahead and classify -3 as a whole. How do we know that 1 is a vertical asymptote? What's special about this factor of x minus 1? What do you think, Lainey? But not the top, right? Because we'd have a number over 0, and we said that was a vertical asymptote. So notice how this bottom factor did not cancel, meaning it's kind of left over. So that's going to produce a vertical asymptote. So we'll say non-canceling bottom factors are vertical asymptotes. Okay, so we're going to try to factor. If we take a look at the bottom, we can figure out where something is happening. But if we look a little bit further to see whether the factor cancels or not, we can tell exactly what's going on at that spot. Okay, canceling or wholes, don't cancel is a vertical asymptote. So if this x plus 3 canceled, the x minus 1 did not cancel in the bottom, what's special about this x plus 1 that did not cancel in the top? What's that going to tell us about our rational graph? Yeah? That's our x-intercept. That's what we did yesterday, right? Non-canceling factor in the top. Okay, so non-canceling top factors are x-intercepts. And we can see that based off the graph. Okay, we can find an x-intercept. It definitely happens at -1. Okay, so factoring is going to be key for these rational functions. Once we factor, we can take a look at what the factors actually are, whether they cancel, whether they don't, are they in the top, are they in the bottom, and that's going to tell us what's going on with this graph. Let's see. What if, this is going to be new for us, they told us that the y value of the whole was 1/2. Okay, thank you. And we already know that where the x value is, right, at -3. How can you find a y value if you know an x value? Plug it in, okay? Now the issue is, if we plug in -3 into the original function, we know we're going to get 0 over 0, right, because we have a whole. Clearly that's not 1/2. So instead of plugging in -3 into the original, what if we plugged -3 into the factors that were left? Meaning after we canceled that whole out, what if we plug in -3 into these remaining factors? So -3 plus 1 would be -2, and -3 minus 1 would be -4. That simplifies to 1/2, right? So if you want to figure out the exact coordinate of that whole, okay, notice how we only get the x value if we look at the factors. But if you want to get the exact coordinates, we can plug in that whole location into the remaining factors that are left. So we'll say plug x value of whole into remaining factors to find y value. Okay, the y value of the whole is pretty important because in terms of the range, we have to skip over that spot. If you take a look at the previous examples, notice how we had 7/5 and 1/2. Okay, we had to skip over that y value. So it's pretty important for us to kind of figure out where that is. The last characteristic I want to go over is a little tricky for us to identify, at least for now, and we're going to talk about it later on in this unit, but it has to deal with the horizontal asymptote. So I'm going to kind of scroll this down for a moment. Notice how for the first one, the horizontal asymptote was at 2, and for the second one, the horizontal asymptote was at 1. can you find a connection between the equation itself and where the horizontal asymptote might be located? The top one was at 2, the bottom one was at 1. Is there some way we can look at the function to figure out where those are? Yeah. Okay, so the a value meaning the leading coefficient. So notice how this was 2 and this was 1, right? Now, since this is a fraction, we also should take into consideration the a value of the bottom because we're dividing. And it was 1 in the first one and 1 in the second. So 2 divided by 1 would be 2. 1 divided by 1 would be 1. Okay? So that's where the horizontal asymptote is coming from. That's not always the case, though. Okay, we'll see an example of that in a little bit. But we do have to be careful. So sometimes that works out, sometimes it doesn't, and we'll spend more time with that in a future section. Okay? But for now, we're going to write down the horizontal asymptote. Thank you. Is the division of the leading coefficients. In parentheses, I'm going to write sometimes. Okay, not every case is going to be that way. Okay, but sometimes it works out. So yesterday, we looked at the division of the constant terms. That gave us the y-intercept. So now maybe we can look at the division of the leading coefficients, and that's going to give us a horizontal asymptote. I wasn't lying when I said there's a lot of characteristics, right? Poles, asymptotes, x-intercepts, y-intercepts, horizontal asymptotes. Okay, a lot of things going on. Let's go ahead and try our next one. Might be the last one for today. Okay. Here's a function. Here's a graph. They tell us the hole where it's located. Let's go ahead and check out some of these characteristics. Can we do rapid fire? Just shout it out. As we go to the left, what are we approaching? 0. To the right? 0. Look at us go. -2 from the left. 1. Okay, the height of the hole. -2 from the right. Also 1. If it's a hole, the left and the right have to be the same because they're meeting up in an open circle. -3 from the left. Negative infinity. -3 from the right. Positive infinity. Good. Okay. Here's an example of where the division of the leading coefficients is not the horizontal asymptote. Notice how if you took 1 from the top divided by 1 from the bottom, that would not give you 0. Okay, so it doesn't work every time. Okay, maybe you notice why this one doesn't work. Okay, you have an idea now?
I was going to say, what if you just assumed it was 0x squared plus x plus 2 and then 0 over 1 is kind of like 0?
Oh, so really, this is like 0x squared plus that, and then you did 0 over 1, that'd be 0. Now, what's the assumption you're making there?
That they're always going to be like x squared is x plus something.
Okay, so they're going to have to be matching degrees, right? If you have a power of 2 and a power of 2, they have to match. If we look at the previous ones, okay, power 2, power 2, power 2, power 2. So if the powers or the degrees match, maybe we can do that division. But if they don't, we're kind of out of luck or we have to fill it in. Okay, we're going to get to that in a future section, but that's great that we're noticing it now. Let's check out the domain. So in terms of our x values, we're going to go from negative infinity to positive infinity, but we have to skip over the x locations of the vertical asymptote and the hole. And when we look at the graph, the vertical asymptote comes first. So we'll skip over -3. And then the hole comes second. So we'll skip over -2. For the range, we're going to skip over the asymptote and the hole again, but instead of using the vertical asymptote for an x value, now we're going to have to use a horizontal asymptote for a y value. So going low to high, the horizontal asymptote comes first. We'll skip over 0. And then the hole comes second. The height of the hole is 1. There's our domain and range. Pretty quick, right? Now that we know what we're looking for. Okay, we'll save the last one for tomorrow, and then we'll take a look at a few more examples.
tool set.